Hello viewers, assalamu alaikum. Today we will discuss about the torsional stress of a beam section and design the beam section for shear and torsion together. Okay, let's start after the intro. Okay, here is problem. A typical beam layout plan partial of shear beam section with a sub beam as shown in figure. The SB 4 meter long would carry a uniformly distributed load of 30 kilonewton meter and produce the torsion and shear force 150 kilonewton. The cross section of beam 250 millimeter by 600 millimeter. The main beam 6 meter long and design the main beam for shear and torsion. That is the section plan. A sub beam 4 meter long carried 30 kilonewton meter distributed load connected with a main beam 6 meter long. The cross section of the beam 250 by 600 millimeter. Step 1, we analyze the beam section and find out the design torsional moment. Here the negative bending moment creates here the torsion. Okay, find out the negative bending moment. Here the negative bending moment, it's as like cantilever. Here negative moment WL square by 2 equal to 30 into 4 square divided by 2, that is 240 kilonewton meter. So here 240 kilonewton meter torsion resist by 2 support. So that is the half 120 kilonewton meter, and here also 120 kilonewton meter. So design torsion is TU equal to 120 kilonewton meter. Now check for torsional stress. Tau u is less than equal phi tau u. So tau u equals to TU divided by 2A0 T. Here A0 equal to 0.85 B into D, and T equal to B divided by 4 to 6. Okay, tau u equal to TU 120 design torsion 120 into 10 to the power 6 Newton meter to convert kilonewton meter to convert Newton millimeter. So 2 into 0.85 250 into 600 into 250 divided by 4, that comes 7.52 Newton per millimeter square. Now allowable allowable torsional stress according to ACI 11.5.1 phi tau u equals to 0.1 phi of 0.33 root over f prime c. Assume f prime c equal to 30 MPa and Fy equal to 420 MPa. So 0.75 into 0.33 root 30, that comes 1.35 Newton per millimeter square. Here tau u is greater than phi tau u, so not okay. So the section is to be increased or torsional reinforcement is to be provided. Now check for normal shear. Normal shear stress equal to VU divided by B into D. Normal shear force 150 into 10 to the power 3. It also convert kilonewton to Newton. B 250 and D 600 minus 60 mm cover. So here comes 1.11 Newton per millimeter square. Allowable shear stress is ACI 11.2.1.1. Phi BC equal to phi of 0.17 root over f prime c. 0.75 into 0.17 root 30, that comes 0.69 Newton per millimeter square. Here also normal shear stress VU is greater than phi BC, so not okay. Shear reinforcement is to be provided. Now check for shear and torsion. Together. VU plus tau u is less than equal phi of 0.17 root over f prime c plus 0.66 root over f prime c. So that's equal to 0.75 0.17 root over f prime c means 30 plus 0.66 root 30 equal to 3.41, that is less than vu plus tau u equal to 8.63 Newton per millimeter square. So not okay for shear and torsion together. Now design for shear and torsion together. AV divided by S plus AT divided by S equal to VU minus phi VC divided by phi Fy d minus d prime cot theta plus Tu divided by phi Fy A naught cot theta. Here AB is equal to 2AST. 2AST. AB divided by S plus 2AST divided by S. AB is equal to 2AST. AB divided by S plus 2AST divided by S equal to, here we will design as a word design for shear and torsion together, so phi BC will be neglected. So 150 into 10 to the power 3 divided by 0.75 into 420 into d minus d prime, d minus d prime, d means 600 minus 6 t minus also 60, and that is both side cover, and cot 45 degree, cot 45 degree means 1 plus tu 120 into 10 to the power 6 divided by 0.75 into 420 into a naught 0.85 250 into 600, and cot 45 degree also 1. So AV divided by S plus 2AST divided by S equal to, that comes 0.99 plus 2.98. So not for normal shear requires this reinforcement and torsion require this reinforcement. So we can say 2AST divided by S equal to 2.98. That will be boxed for torsion reinforcement. Now from here we can say A S prime divided by S equal to 0.99 plus 2.98. AB plus 2AST, assume AS prime. That means A B divided by S plus 2AST divided by S equal to AS prime assumed. AS prime divided by S, AS assumed. So here is 3.97. Here we use 4 leg shear stirrup. That means 1 leg, 2 leg, 3 leg and 4 leg. 4 leg is effective for shear and torsion, and use 10 mm bar. So area of 10 mm bar equal to 78.5 millimeter square. So here we will use the 10 mm bar. Four into 78.5 divided by S equal to 3.97. So S equal to 79.13 millimeter center to center. That comes up 75 millimeter center to center. 75 mm center to center reinforcement is provided all through the beam section. 75 mm reinforcement is to be provided. 75 mm all through the beam. A extra reinforcement is required for torsion. Due to torsion, a beam section creates a two opposite direction axial force, like this direction and also this direction creates a force, and this force creates a this like of stress and develops a crack due to tensile stress but tensile force. So to resist this tensile force, a extra longitudinal reinforcement is required. So AL is equal to AST divided by S into P perimeter of the section into FYT, that means reinforcement yield strength of torsional reinforcement, and longitudinal reinforcement yield strength Fy into cot square theta. So the yield strength of torsional reinforcement and yield strength of longitudinal main bar is same, so that is 10:1 or 1, and cot square theta means 1. So that is the 2 AST divided by S equal to 2.98. we will find inch square. So here is 2.98 divided by 2 into perimeter of the section 2 into 250 plus 600. So here required 2533 millimeter square. And the long of bar is equal to 2533 divided by pi by 4 into 20 square. So approximate 8 notch bar. If you use two phase two phase, the 4 notch phase bar is required for two sides. Okay, here 4 notch, 3, 4, and here also 1, 2, 3, 4, and here also the top phase bar, and here also the bottom bar. So viewers, that's all.